not what you need. Sorry, it's not just what you need.
Where are you going to start?
You need something else with DCC.
Well, I'm showing it that it's going to DCC HNR2.
You need DCC with.
HNR2.
You have HNR2.
Alright.
You've got an amine.
This is backwards.
It's just backwards.
Oh my gosh.
Any of those reagents can be written over the arrow. It depends on what you have.
Gosh.
Draw it in. What carboxylic acid do you need?
Wow.
Okay, so I just started the recording. For those of you watching the recording, we have just worked on the synthetic pathway. How was that experience for you guys?
Incredible.
Does it feel like getting new gears moving? You have to make decisions about how to draw a structure. You get a lot of choices on what reactions to have. Some of you decided on hiding 3 pieces that left a lot of room for ambiguity if you pass it off, right? Like you would give the first starting material and the first reagent, but not the intermediate. That can be predicted, but then not the next reaction and not the reaction after that, in which case the person you gave it to basically gets to choose your own adventure, and there's no one right answer. What I often do is take the starting material and the final product, and I leave the intermediates and the reagents blank, and you have to decide, what can I make the final product from? What can I turn the starting material into? How do those 2 things overlap? And there were still a lot of right answers for the ones that you guys came up with. So I gave you this starting material, this product, how can I solve it? This starting material, this product, how can I solve it? Jacob, you solved this one, and I think you worked backwards first. Is that true?
Yeah.
You recognized the alkene formed, and from unit 4 with aldehydes and ketones, we said that alkenes can be formed by the Wittig reaction. The ylid reacts with an aldehyde, and I can see this carbon chain, this little isopropyl group and a carbonyl. Isopropyl group, this would have been a carbonyl carbon. Now it's an alkene carbon because of the Wittig reaction. And so this must be the aldehyde that synthesized it. Remember, only aldehydes and ketones, none of our other carbonyls. So then we just needed to partially reduce the amide. And Maddie was asking this question, what intermediate does the dibol give us? Dibol gives us this alkoxide, and the alkoxide gets protonated to become this amine-ol, a gem-amine-ol. And that's basically a hemi-imine. That's halfway between formation of an imine from an aldehyde or hydrolysis of an imine to an aldehyde. So in acidic conditions, the next step here is protonating the amine and then kicking off the amine and getting to a protonated aldehyde before that gets protonated. So the dibol partial reduction is actually part of the imine, or it kind of co-ops part of the imine mechanism. In order to get rid of the nitrogen, we turn it into this gem-amine-ol, and then we can hydrolyze the nitrogen away. Great. In the bottom one, I screwed up at first. You guys on the camera don't know that. What we see is a nitrile attached to this cyclopentyl group, and then an amide that has this methyl cyclopentyl, or I should say cyclopentyl methyl benzamide. That means that this group, the cyclopentyl, has to be this cyclopentyl, which means this carbon here of the nitrile must be this carbon here connected to the amide. So we need to create an amide, and that means having a carboxylic acid intermediate reacting with an amine, and here's what that amine must look like. Actually, does it need to be a carboxylic acid that reacts with the amine? to form the amide?
It can be any.
Not ether.
Well, this isn't.
It could have also been an acid chloride. I could have used, instead of benzoic acid, I could have used benzoyl chloride and provided an excess amount of amine. I could have also used an anhydride and used an excess amount of amine. And technically, you can use esters as well, because esters are more reactive, amides are more stable. You can convert the ester into an amide by aminolysis, reacting with an amine. But the carboxylic acid, the acid chloride, those would be the most feasible ways. That's what somebody would do in a lab. So getting this amine from this nitrile reduction, reduce the nitrile to a primary amine. Do you guys have any questions on this activity or on these examples in particular?
If you wanted amine to be on the top right product, where the amine originally was, could you have just done the Wittig reaction?
If you wanted, I'm sorry?
If you want an NH2 group on the right side, could
Here?
yeah, instead of a hydrogen, could you have just done
The Wittig reaction doesn't work with these other groups.
You can only have an aldehyde.
Aldehyde ketone.
Okay.
Aldehydes and ketones work well with the ylid. And by the way, we can rewrite the ylid another way. This one's a little bit spelled out. But we can also draw the ylid like this with more bond line structure character. And what are your options for an ylid? The world is your oyster. In class, we looked at the ylid that was a CH2 group. But you could also have an ylid that is part of a ring system. Okay, there are a couple of things that I want to get at today. Mechanisms, and then also the use of acetal as a protecting group in synthesis with other carbonyls. Do you guys want to look at mechanisms first or acetals as protecting groups first? Any preference? Let's go through mechanisms. You've got a worksheet for mechanisms. We have hydrolysis of esters and also Fischer esterification, acid catalyzed esterification. I didn't necessarily do it intentionally, but let's look at hydrolysis of the ester first, since that's on the front page. Does this have more steps? I'm going to rephrase this, sorry. This is acid catalyzed hydrolysis. Does this have more steps, less steps, or the same amount of steps as the acetal hydrolysis? Sorry? Acetal hydrolysis had 7. This has 6. So this is 1 step shorter. The acetal mechanism is the longest one you'll have unless there's like an EAS or NAS that has a bunch of resonance forms, you know. Anybody recognize this ester? Oh, okay. None of you are taking the lab this semester? This ester gives a fruity smell. Yeah, we call it banana oil. Isopentyl acetate is the banana oil that you guys synthesized in lab. One of the reasons you might not have gotten 100% yield of banana oil is because some of the products with isopentyl acetate is H2O, in the presence of an acid, which means that some of the product can hydrolyze as it's formed and reverse the reaction. This can limit yield. It's an equilibrium problem that makes it really hard. Am I in acidic conditions or basic conditions? Acidic. What is my acid? Hydronium. What is my base then? Water can be a base. What else could be a base?
I'm wondering about the acid. Is it just any inert acid? I think that's the right word.
H3O plus is formed by sulfuric acid dissociating with water, or acetic acid dissociating with water, or tosylic acid dissociating with water. We could have shown TSOH, ACOH, we could have shown H2SO4, but if they're in water, this is the acid that we're probably dealing with. Deal? I'm sorry?
What are they called? Like the HCl, HBr, those types of acids?
HX acids, hydrohalogen acids. So I want to touch back on what is the base. It is possible that water acts as a base, but that just forms hydronium. It is possible that the oxygen of the ester linkage, acts as the base, but that doesn't actually help me do anything in this hydrolysis mechanism. And it's possible that the carbonyl oxygen acts as the base. In fact, if the carbonyl oxygen acts as a base, there becomes resonance between the two oxygens in the carbonyl. Resonance delocalizes a positive charge, which means that this is the best base possible in the structure. So this is what I want you guys to ask. What is my acid? What is my base? I'm in acidic conditions, so my first step should be protonation. What will the acid react with? I want to ask you guys a question actually before we get into this too much. Let's label these 3 oxygen atoms. And I'm going to keep another molecule of H2O here as we go through this. I'll have H3O plus and H2O. Which of these 3 oxygens do you think will be the alcohol oxygen at the end? Is it A only, B only, C only, a mixture of A and B, a mixture of A and C, or a mixture of B and C? Any idea? Let's keep our eye on the oxygens as we go through the mechanism, and let's see which oxygen actually becomes the alcohol at the end. All right? First step, protonation. By the way, I'm drawing my hydronium a little bit different than I normally do. I typically draw this as HOH2+. And it's because I'm finding that students, I think, understand what's happening better when hydronium is drawn out completely. I like to draw it like this because it highlights the acidic bond and the fact that water is the byproduct. To each their own. Remember, bonds form from the more negative atom and bonds break towards the more negative atom. My second step, after protonation, what has that protonation just done to my carbonyl? Has my carbonyl become more electrophilic or less electrophilic? It's become more electrophilic because oxygen wants its electrons back more than ever. That means I'm ready for acyl addition. Acyl addition means a nucleophile attacks. What is my nucleophile? One more time. Water. Is water a good nucleophile or a weak nucleophile? Which makes it all the more important that the carbonyl is protonated. Water is a weak nucleophile. It won't attack unless the carbonyl has been protonated. Water attacks the carbonyl. The CO double bond breaks up to the oxygen. Once again, I'm expanding this water that has attached. You don't need to. All you have to show is OH2+, although if you're not doing stepwise, if you're doing fully in series, you might want to put OH with a bond spelled out OH, because we're going to need to deprotonate next. One more structure that I need to draw on the right-hand side. What is it? Water. I drew two molecules of water. On the left-hand side, one of them attacked. The other needs to show up. Yes?
Do you know which bond breaks first on the acyl addition? Does it matter?
What do you mean which bond breaks first?
Does the oxygen push onto that carbon, or does the oxygen pull its pi bond away from the carbon?
Oh, there's only one bond that breaks, and there's one bond that forms, and they happen at the same time. That's why we show it as one step. After acyl addition, what should I do? I've got this protonated structure. I should deprotonate. Now, I've got an OH and I've got an OH2+. What group should I deprotonate from? More positive charge, more acidic. Water is my conjugate base. So water here takes a hydrogen and breaks the OH bond back to the oxygen. Does this structure remind you of anything? It looks like a gem diol. And the gem diol was one of the hydration mechanisms we looked at, right? Aldehydes and ketones hydrate to gem diols, which means we're looking at something very similar to that. It also might remind you of this functional group. Not an ester. It is an ether and an alcohol on the same carbon, a gem etherol, hemiacetal. So we're in kind of this similar situation to our hydration mechanism and our acetal mechanism. All right, after I protonate, the best thing to do, I haven't drawn my conjugate acid. What is my conjugate acid? H3O+. Now that I'm back in acidic conditions, best thing to do is protonate. What should I protonate this time? Should I protonate one of the OH groups? Good. The OH group would just send me backwards. So the only logical thing to protonate is the ether oxygen, or what used to be the ester linkage oxygen, carbon B. Yes, sir?
Because it's more stable? It can handle the extra bond?
No, they're equally stable. What I'm trying to do right now, sir, is show what steps must be done to get to the final product, not what steps this molecule actually goes through. This little molecule is getting bumped around between solvent molecules and acid, and it can be bumped any which way on its reaction coordinate diagram, I'm showing what must happen in order to get to the final product.
If it fails here, it just goes back to like step 1 or 2 and keeps going until it gets it.
That's right. We just keep going until it gets it. Step 5. Think back to the hemiacetal mechanism because this is not so different. After I got one of my groups protonated, what did I do? Elimination. I'll kick off the group I just protonated. Elimination reforms a carbonyl. Does it matter which of my OH groups reforms the carbonyl? Does not matter. They're identical. Either one could form the carbonyl. Now this protonated ether gets kicked off. I'm sorry, I forgot to draw that. I've still got that molecule of water floating around. That gives me this isopentyl alcohol and a protonated carbonyl. Can you tell me which oxygen of the carbonyl is protonated? Is it the CO oxygen or the OH oxygen? Which oxygen of the carbonyl is protonated? The CO double bond oxygen? I think I said that weird. CO double bond oxygen or the OH oxygen? Okay, it might be fair to say they're both protonated because they both have a proton. That's totally fair. But the OH is always an OH in a carboxylic acid. The CO double bond is usually just a CO group. It's the carbonyl oxygen that is protonated. That should remind you of every time acid-base chemistry happens with a carbonyl, it's the carbonyl oxygen. It's always the carbonyl oxygen. Why? Because there's resonance when the carbonyl oxygen is protonated. There's no resonance if the other oxygen is protonated. I ran out of space, but my last step is deprotonation. Get me to that final product. What is my base in this step? Water acts as my base, which reforms my catalytic acid. H2O. By the way, I need you to show this OH bond. If a bond is going to break, you have to show it. What questions do we have?
Are the products alcohols?
One product is an alcohol. One product is a carboxylic acid. And I regenerate my catalyst H3O+. Cameron.
On step 5, I see that the OH in the middle, that was the ester linkage,
Yep.
is gaining that electron with that red arrow.
Yes.
But there's only one oxygen there. How in the product of step 5 is there 2 OH groups?
Well, here's OH, here's OH, here's OH. This OH is now leaving to become an alcohol.
And then the top, I see.
And then I still have an OH that's not doing anything, and I have an OH that's forming a double bond. So this has 3 OH groups. Technically, this is ROH, ROH, RORH+. But there are 3 oxygens. All 3 of them have hydrogens. 3 oxygens, all 3 of them have hydrogens. Good question. All right, what's the answer? Which of these oxygens became the alcohol oxygen? B only. And B was the ester oxygen. What about the carbonyl oxygen? Was it A or B only, or was it a mixture? I'm sorry, A or C? Was it A only, C only, or was it a mixture of the 2?
Mixture.
Why can you say it's a mixture? How do you know that? Even before step 5, right? It's actually more like at the end of step 3, can you keep track of which oxygen was A and which one was C? Not at all. All right, now how would we prove that experimentally? If I wanted to use instrumentation to prove that were true, any guesses on what might help me? This mechanism is plausible, but someone might say, no, I'll find another way. I'll find another way to kick off a different oxygen. Could anybody suggest a way to map those atoms and watch them move through the reaction? Heavy what? Heavy water. Heavy water is D2O. So I'm not sure how would tracing the hydrogens help us know how the oxygens are moving?
I don't know.
If it's mass spec, how do I tell apart the oxygen atoms? If it's NMR, how do I tell apart what groups?
Could you do a non-oxygen acid and do a halogen instead, and then a halogen would form instead of an alcohol?
No, because halogens won't behave like that. The halogen nucleophiles aren't as good as the water nucleophile here. Isotopes of oxygen? Are you a biologist? Can you tag it with a fluorescent gene?
That was my first thought too.
Yeah, like can I make an oxygen fluorescent, just follow it and see what the stereochemistry would be over time?
It actually, well, the problem is molecules usually fluoresce, not individual atoms. But I like that idea. And the answer actually is isotopic oxygen. What you can do is, most oxygen has what atomic mass?
16.
16. So you can run a reaction either forward or backwards where you map one of these with oxygen 18. And then you can look for the NMR signal of oxygen 18. Or I'm sorry, I think maybe I need to look into this. I think it's actually oxygen 19. Look for the signal of oxygen 19 in the products that you get, and you'll find that it only ends up in the alcohol. So it is isotopic labeling, isotopic tagging, and then we actually use NMR. So a combination of all of those things. We could have also used isotopic labeling mixed with mass spec and looked for that heavier oxygen as opposed to the lighter oxygen. That's how plausible mechanisms get validated with experimentation. It is all equilibrium, all of it. And what equilibrium means is when you look at the reaction coordinate diagram, 1, 2, 3, 4, 5, that wasn't even enough steps. It just means that if you get enough energy to push your molecule here, it might go forward, it might go backwards. It might go forward again a little bit further, and it might go backwards a little bit further. Every single step is in equilibrium. And so if you're trying to push everything to the final product, increase the amount of starting material that you have. So that Le Chatelier's principle says it will shift to the products. Or pull out the product as it forms, and then Le Chatelier's principle will shift more to the products. One of the best things is to just provide more and more heat so that you get this chance of everything ending up on one side, but again, at a certain point, it still can go backwards too. All right, I'd like for you guys to take a small break, so feel free to get up and move around and get your legs stretching. 5 minutes max, and we're going to come back in and look at the Fischer esterification mechanism, the backwards of this.
Oh, I think it's. Sorry, keep walking. Animal fats or waxes they have an ester in the middle. So when you put acid on an ester, you're turning it into acid and alcohol.
Yeah.
So you're
A lot of animal fats have triglycerides like this.
maybe it's plant fats then that have esters.
Those are esters. It's a triester. And if you hydrolyze this, then you
Only esters. Yeah.
you end up with a triol and 3 equivalences of acids.
So what is if you have
Yes. Show your lone pair. Since we are showing it come from electrons, we only need to show relevant ones, and it's relevant here.
Because for my second attempt, I started with this,
Mhm.
and I knew that would become an OH here, but on the double bond, I just felt like that was breaking.
Rules.
Yeah, I was like, that can't be right.
In fact, it feels
This
uncomfortable,
chapter-
but that's what makes the carbonyl even more willing to accept electrons.
21.
Because now that double bond will want to break a lot more.
Probably 21 since
And
we're
your charge.
test.
It's gonna be positive.
Good.
Is this chapter 21?
And 20, yeah,
20 and
20 and 21.
Okay.
They blend together. Well, it depends on what textbook you're looking at too.
Yeah.
And so for acyl addition, is acyl addition still next?
Yep.
So then I have to break the pi bond.
When a bond breaks, it always goes to the more electronegative atom. Is that oxygen or carbon?
Oxygen's more electronegative.
Good.
So the pi is gonna break to the oxygen.
Correct.
Taking away that positive charge, so there's gonna be a positive charge here.
But that's not going to be the only thing that happens. So we'll never actually see the positive charge. When this bond breaks, this group attacks
The whole thing.
just the oxygen. Just like the oxygen here attacked the hydrogen, the oxygen here will attack the carbon.
But the whole group goes to it.
That's true.
Including this hydrogen.
None of these other bonds are going to break.
That's why the next step is gonna be deprotonation.
Correct.
You have to take that hydrogen.
That's right.
Okay.
You've got it.
Oh my gosh.
And you know, Cameron, your mechanism was all logical.
Because I feel like I've got like the concept of the mechanics of the mechanism down, but not
Yes.
necessarily what it's supposed to do.
Correct.
Which is
Yeah. You
Not
knew which way your arrows should go. You knew which bonds to break, which bonds to form, in a way that gave you the product. But it wasn't. Yep. And does it help you to repeat step by step, or does it help you to do something fully sequential?
step by step makes my brain think way better.
Good. Just takes a little bit more time when you're doing pen and paper. That's the only difference. By the way, everybody good with this? Can I erase it? All right.
Is it more efficient to take product out that you don't want to push Le Chatelier's principle, or
Is there a way to do it?
like is it like what would you say is like more efficient way to do it? Is it like removing
Adding excess?
product or adding excess? Is it or does it matter?
Sometimes it depends. In OCHEM 1, you did the dehydration
Mhm.
of 4-methyl cyclohexanol. There was only one starting material, so you can't add an excess. But that forms an alkene and water in acid, which can give you acid catalyzed hydration
Mhm.
back to the starting material or structural isomers.
Yeah.
So you have to pull those products out of the acid mixture as they form. Otherwise, you get a really terrible equilibrium in your yield.
Yeah, I do remember that.
So that one was pulling it out, but it's feasible to pull it out because the starting material has a very high boiling point, and the two products have an equivalent boiling point.
Yeah.
So it's very easy to pull them out. Sometimes you have two different products whose boiling points are both lower than the starting material, but are different from each other, in which case you only pull one out, and that can still sometimes be useful, because you'll still shift to change that equilibrium, shift to increase that concentration, and you kind of lose the ability to do the reverse reaction.
Yeah.
But then you still have to do an extraction to like get the product that remains out.
Yeah.
Unless you're lucky enough that the product that distilled first was the one you wanted. Other times it's less feasible to pull them out during the reaction, and so it's better to just have an excess of one reagent. The esterification reactions you guys are doing in lab, what is your excess reagent? The acid or the alcohol? The alcohol also serves not just as the excess reagent, but as the solvent. So those two roles are done at once. It is a solvolysis reaction, a reaction with the solvent. So by having it be the solvent, it is the excess reagent. That already is doing a big lift. You've got so much of the starting material, and that helps push equilibrium forward. If you tried to run esterification in some other solvent, like acetonitrile, where acetonitrile is not going to react, but the alcohol and the acid can react to form the ester in water, then you might feel an even worse equilibrium because you've got like even amounts of starting materials and products, both in acid, able to go forward and backwards. But when you use the alcohol as the solvent, equilibrium shifts to the right to give you a better yield. And still the yields are challenging.
Yeah.
If you're losing your solvent, if your solvent's evaporating away, will your reactant start crashing out of solution?
Yeah.
So you can use the crashing out of solution to know if you need to add more solvent.
Yeah, but usually at those high temperatures, the amount of solvent needed to dissolve the amount that you have is very small. Do you remember in OChem 1 when you did the zinc iodide lab? You took zinc and iodine, you mixed them together, and you made zinc iodide aqueous, and then you boiled off the water to get rid of the water and leave just behind the salt, zinc iodide. There's a moment where it looks like you've got a milliliter of water plus something like a gram's worth of zinc iodide, and it's just water, and then all of a sudden, it literally sounds just like that. It sprays this solid all over the place, and there's no water left. So if you're banking on the fact that it's going to start crashing out, it might crash out all at once. It might not be close enough to be like, oh, I need to add more because I'm starting to see it slowly come out. But you could monitor it and say, like, I started with 50 mils and now I've got 10. I'm going to add more solvent to get back up to 50 because my solvent is evaporating.
Bigger stopper size.
Are there bigger
Yeah.
addition funnels? Or set funnels?
Yeah.
Yeah, but they don't always fit the rest of our glassware. We have bigger ones, they just don't attach well.
So I don't know if your experiment, but we have these ones by like necessity, and I don't recommend them. I would try to keep it in the small ones, but all possible.
Are you talking about the reaction flask? The round bottom?
No, I'm talking about the squeeze.
Oh, while doing the
Yes,
extraction.
Yes, I would say
Was
try to
it-
keep it in the small one, the big one is not fun.
Yeah, it's true.
Were you guys doing wintergreen or
I
Lindsay green?
but I would just avoid the large one.
Do you guys want to try this one on your own? I do want to remind you that H+ is a challenging acid to work with, mostly because of its conjugate base. So it's useful to use an organic acid like tosylic acid or acetic acid. It is the same number of steps, and I think the steps are actually in exactly the same order. Which means all you have to pay attention to is what group should be being protonated, what should be deprotonated. And I want you to pay attention to the one we just did, so that you can learn from it, lean into it. What I'm going to do is periodically, I will draw the intermediates, but not the arrows, so that you can at least start seeing what arrows might be necessary. I'm going to use toslic acid here. You can use H+, but then you don't have a conjugate base. So H+ can be generated from TSOH. Right. H+ is toslic acid, if you want it to be. Why might I not want acetic acid as my acid in an esterification mechanism?
You make the opposite. You use the alkyl group of the acetate.
Acetate is a carboxylic acid, and it might be esterified instead of the carboxylic acid I want. Go ahead and show your relevant lone pairs. So there's a lone pair there that's attacking. That's where your arrow should start from. Thank you. This is an intramolecular reaction. So one part of the molecule will attack another part of the molecule. Good. Dibol attaches here to the carbonyl carbon.
This is an H. This is dibol.
That's the H from dibol.
Does this go back into dibol? When you go from this type to this?
Dibol becomes an aluminum waste product.
Then you're just left with an acidic solution. Because you have
In the aqueous workup.
before you get here, you have to go to here.
Yeah, this just gets deprotonated into this.
Where does this hydrogen go?
Water. Water takes it to reform hydronium. Acid catalyzed hydrolysis.
So this H is from the. This takes the.
This H from dibol is here. It's the aldehyde H.
Oh. Wow.
There you go.
Can we bring these papers on the exam? Like all of them?
No, you can bring one cheat sheet, front and back. You can put whatever on there you'd like to. Good job. What you got there? Yeah, you got enough. Yes. Where's the positive charge?
Oh,
This positive charge? Where is it now? Well, let's notice this structure. I've got OH, OH, ORH. Let's find a structure here that has OH, OH, OR. Not quite. OH, OH, ORH.
Oh, the,
The oxygen with 3 bonds has the positive charge.
okay.
There you go. And that tells you where deprotonation happens next.
Okay, thank you.
Mm-hmm. Oh, I don't want this to attack. Do you remember, Maddie, that we said the oxygen of the ester was the oxygen of the alcohol?
Does this reaction need water?
No, this reaction should be void of water. Water will hydrolyze any ester backwards. I don't want this base to attack. That won't help me get anywhere. Now I've lost my conjugate base. Remember that the oxygen of the alcohol becomes the oxygen of the ester, so my alcohol needs to attack. That's the acyl addition. Or compare it to our last reaction. We said in the hydrolysis that we protonate this and kick it off. So now in the formation, this needs to attack. Great.
Does this make sense?
Yes.
Okay.
When you use H plus, that is your conjugate base. Nothing.
Okay.
It leaves behind an H plus.
Gotcha.
Good, good, good. Yeah, you can say that for sure.
Would the other one just be the
Or it would just be H2O and H plus.
gotcha?
Mm-hmm. So it's a common mistake, but this is my base. So I don't want to lose it. Instead, what I want to make is the alcohol attacking the carbonyl. That's actually what you just erased. Keep that. We're going to be breaking open the carbonyl, acyl addition. You just chose the wrong nucleophile. I want the alcohol to be a nucleophile to the carbonyl. Perfect. Perfect. Great job. Yep. Yes, exactly. Well, except you lost. Oh. You gained an oxygen somewhere. You went from OH to OH2. It's OH to OH. One hydrogen. Now there's 2. So now there's just 1 hydrogen, and then you pull it off. No hydrogen. There you go. You got it. Perfect. Yes. 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 You're 1 step away, Louise. Good job. Hydrogen doesn't own any electrons. Oxygen wants to bond to the carbonyl. Also, carbon doesn't own these electrons. Oxygen owns the electrons. Yep. Yep. When a CO bond breaks, it always goes to O. Show the lone pair. You got it. Great job. I don't know what to give you to do for the rest, but I don't want you to read because I got more to tell you. I realize I forgot to draw my conjugate base here. Great job on the first step. Don't forget to show your lone pair on this oxygen. How big of a ring does this form? 1.
Yeah, that's
Okay.
It's 4 carbons, but the 5th one makes
Good.
great, great, great.
You forgot the OH plus here, but you had it here.
Yeah.
Good. 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 Great. Just one step away. Great job. Nailed it. Where did you get that to? This is not a good leaving group in acid. It needs to be protonated first.
So it does have this?
You just kicked off O minus. Yep. What did you have before this? Can I see? Yeah, you protonated it.
Okay.
Although you didn't show the OH bond breaking,
Oh, here.
but it,
From
but it
this.
does. Yep.
Yeah.
So this OH bond breaks, and then you get a protonated group. That's a good leaving group.
Okay.
So you got
So that's my
OH2 plus. Good. No negative charges in acidic conditions. The only negative charge should be on my base. I don't want this O minus. Negative charge should be drawn to positive charge. That's the HI1D protein. Just like this. This is the form we want to get next. Yep, exactly. Now how do I get back to the ester? Nailed it. Good. All right, for those of you that have finished, I want you to consider this synthesis. For those of you that have not finished, do not worry. We're not done yet. Two steps. Not including aqueous workups. Those of you on the mechanism, stick on the mechanism. We'll get to this one together. What step are you on? Which is? Right? Don't forget to use those as guiding guidance on what should happen next. Perfect. Who wants this bond? Yes. There you go. Yes. Perfect. Cameron, you just came up with that on your own. I didn't give that to you yet. Great job. Did you got it? Yep. Yep. Nailed it. Great job. You're good, James. Right? Good, Killian. The only thing you're missing here is the OH bond breaking the O. Okay. Feel good? Yep. Okay. Oh, I said 2 steps. I think I might have meant 3.
Have these mechanisms been proven?
Like I said, the isotopic labeling.
They proved it already? It's not.
Yeah, it's not a guess anymore.
Is there any actual benefit to proving the mechanism? Is it just like
We
knowledge?
understand better like how atoms will behave and interact with each other. And now we can apply it to novel molecules, novel syntheses. My job is not to get you to be able to the novel synthesis. My job is to get you to understand the ones that have already been proven, so that if you go on to that, you have the background for it. You know? I'm thinking 3 steps. It depends on how you write it. You might call it 2. It depends on how you write it. You might call it 3. There are better and worse ways. No, actually, yeah, I guess there's more than one way to get there. Okay, maybe I need to reconsider the structure I give you. I'll give you another one in addition to that, okay? But come up with a solution to that if you can. We'll go through another one that maybe highlights it a little bit better. This guy's not going to leave carbon with a positive charge for no reason. When we see the elimination, we should form a pi bond as well. Because remember, we want to get back to a carbonyl, and this will be the step we form a carbonyl. Oh, nope. No breaking of this bond, just forming.
Oh,
From the lone pair. Yep, good. Perfect. Now I've got a carbonyl. All I have to do to get to the ester is nail it. Positive charge here. Kick them off the wrong group. This OH forms a double bond. This OH2 plus leaves. Which is actually like what you showed. You showed this forming a double bond, but you don't have OH2 plus. OH2 plus. So just this group going off, that group going on. You've got it. You've got it. All right, as you guys wrap up, I'm going to finish this mechanism. All right, if you guys want to listen, I'll describe what happens along each step. Protonation, there are a lot of things that can be protonated, but if we're preparing for acyl addition, there's one thing that is best protonated. Acyl addition happens best when the carbonyl oxygen gets protonated. After protonation, I want acyl addition. I want to point out something I noticed several times, which was in acyl addition, a lot of people thought maybe the conjugate base would do acyl addition. But you'll notice a few steps down the mechanism, that doesn't get me anywhere closer to an ester. I need an alcohol to do acyl addition. That will get me closer to an ester. The issue here was that the alcohol was on the molecule. It wasn't a separate molecule attacking. After I protonate, I'll deprotonate. Anything I'm missing in that molecule? Positive charge. After that, I will reprotonate. Does it matter which of my OH groups gets protonated? No, both would have been correct. I mean, either would have been correct. After that protonation, elimination. Remember we learned in OChem 1 that elimination reactions form a pi bond. This is where I reform the carbonyl. I kick off a molecule of water, and now I'm going to combine these steps. My conjugate base deprotonates the carbonyl, and I get my ester, the water, and my catalytic acid. Some of you showed water as the conjugate base here. I would give credit for that. That's plausible. They say to never teach anything important in the last 10 minutes of class, but you guys said you wanted the mechanisms first, so here we go. All right, this might not be the best reaction to go through for what I'm trying to highlight. But what I want to demonstrate for you is the usefulness of the usefulness of acetals as protecting groups. Are you guys okay if I erase this side of the board? I think you all got this pretty much.
The OH doesn't need to be attached to the main molecule. It could be separate, right?
Correct. Like we saw in our hydrolysis, the alcohol was a separate molecule. Like you're seeing in your esterification projects in lab, the alcohol is a separate molecule. So I gave you an example of reactions that form esters from two different molecules and a reaction that forms an ester intramolecularly, cyclic ester. Oh, I just erased it. Well, whatever. What I notice about my final product is that I want to keep the aldehyde, but I want to get rid of the amide. What reaction allows me to take an amide to an aldehyde? Dibol. Is that what you called it? Dibble. Okay, I like dibol because it sounds like eyeball, but to each their own. If I added dibol here, would it react with the aldehyde? It would preferentially react with the aldehyde because the aldehyde is more reactive of a carbonyl. So if I added enough equivalences, I could reduce both the amide and the aldehyde, and I would get an alcohol and an aldehyde. And I think this is where Jordan was like, okay, well that's fine. I can just selectively oxidize the aldehyde, the alcohol, back to an aldehyde, which is why this was not the best one. What I wanted to suggest here is that we actually take a diol, or two equivalences of any alcohol, and we create an acetal. I no longer have an aldehyde. I have essentially protected the aldehyde from any carbonyl reactivity. We call this a protecting group. It protects aldehydes and ketones. After I've protected it, I can run dibol. The dibol no longer reacts.
Does it leave behind water?
There is a byproduct of water with the acetal formation. The dibol cannot react with the aldehyde because the aldehyde doesn't exist. All right, just for clarity, if I had taken this with dibol straight away, and again, the usefulness of dibol is that you add only the equivalents that you need so that you don't over-reduce anything. The product I would have gotten would have been an alcohol and an amide. Not useful if I'm trying to get rid of the amide. Some people might say that this H3O plus acid workup is enough to hydrolyze the acetal back. What I was trying to go for was that all we do is neutralize, and then we do a hydrolysis step. And by hydrolyzing, we get the aldehyde to return. So again, some people say that this is one in the same. And that there's some truth to that. A situation where you can't use a protecting group. There's actually lots of protecting groups. Alcohols have protecting groups. Amines have protecting groups. Amides have protecting groups. Those are usually a little bit more complicated, and they're just really long acronyms, so they mean nothing to the student. Let's look at another example. Let's say I have this ketone and this nitrile, and I want to get to this diketone. How can a nitrile be converted into a ketone?
Turn into carboxylic first.
Yeah, that'd be a long step. Oxidize this into a carboxylic acid. Reduce it into an aldehyde. Acyl addition to the aldehyde to make it secondary alcohol. Oxidize the alcohol into a ketone. We can actually do it in one step. Grignard, aqueous workup. The nitrile plus a Grignard gives a ketone. What will the Grignard react with? The ketone or the nitrile? Why? How do you decide if a nucleophile goes to one carbonyl or another? Reactivity. What's more reactive? What's a better electrophile? A ketone or a nitrile? Nitrile is the most stable. So if I add a Grignard here, and that Grignard I'm looking for in this case is methyl Grignard. If I add a Grignard in this compound, I keep my nitrile and I get a tertiary alcohol, not what I'm looking for. So what can I do? I can protect. This time, instead of a diol, I'll give you two equivalences of an alcohol. I can protect my ketone. It's now an acetal. It's not a diol. Now that I have that protecting group, I can do whatever I want to with my nitrile. And once again, we run into that situation where some people will say the H3O plus here hydrolyzes the acetal back to the aldehyde anyways. You may want to show that this is the intermediate you get, and then indicate the hydrolysis of the acetal back to the ketone. What I'm trying to get at here is that there are sequences you want to do with the more reactive carbonyls that would be impossible, sequences you want to do with the less reactive carbonyls that are impossible because there's a more reactive carbonyl that will react instead. So we take advantage of its higher reactivity and we turn it into a different group that isn't a carbonyl. And then we do the chemistry with the less reactive group, and then we go back and we replace it. Your synthesis routes for this written work, they kind of do that, a similar process. There's like selective reduction or selective oxidation in those synthetic routes. If you guys get stuck on your synthesis for your written work for the carboxylic acids and derivatives, reach out to me, let me know, talk to each other, try and help each other understand a process that works. A few assignments to keep in mind this weekend. Aldehyde and ketone written work. Carboxylic acids and derivatives written work. 2 written works for this unit test. And the unit test. When is the unit test due? Monday night. Tuesday we'll come in and we'll talk about the unit test and we'll move into our final unit. I know, final exam is really close. So I know a lot of you don't take the unit test until Monday anyways, and that's usually when I see the written work come in. The problem is I have my OCHEM 1 unit test this weekend as well, and theirs is done Sunday night, so I'll be grading that on Monday. So if you wait until Monday to give me your written work, I may not be able to give you feedback on things to correct in your mechanisms or ways to look at your synthesis better. So get it in sooner than later, or reach out to me with a message so that I can reply a little bit quicker. All right? Have a good weekend, guys. Good luck on the unit test.